Our next topic involves a concept called stationarity. We need a time series to be stationary in order for us to apply our various modeling methods that we will be talking about this semester. So to begin here, we're going to talk about two different definitions of stationarity. The first one deals with a strictly stationary time series. And basically what this is saying is as follows. Suppose I have a set of random variables from my time series that are consecutively ordered. And so I'm going to call this x sub t1, x sub t2, down to x sub tk. So we have a length of k here. You might be wondering, why don't I just call it x1, x2, down to xk? And the reason being is because I'm interested in any particular set of times. It could be x1 through x10, or it could be, let's say, x21 through x30. And so this notation of t1, t2 down to tk allows me to do that. Okay, so we have this segment of a time series. Now, if I were to make a h lag shift of those time points, then the probabilistic behavior of both sets of our time series will be exactly the same. In other words, they will have the same joint probability distribution. So for example, let's say I look at x1 and x2. The probability that x1 is less than or equal to c1 and x2 is less than or equal to c2 is exactly the same as if I were to shift up by 9 different points in time. Okay? Now, this is a very, I guess you would say, restrictive thing that we need for our time series, because we're assuming the joint probability distribution is exactly the same. And so, because of that, very often, instead, or most often, we will be working with, instead of strictly stationary, we will be thinking about this in terms of weakly stationary. And what weakly stationary says, okay, let's just look at the first two moments corresponding to these random variables. And these first two moments then are invariant, or they're the same for an h lag shift in the corresponding time points. So in other words, the expected value of x of t is equal to one number, let's call it mu, for any time point. Also, then the autocovariance for x of t and x of t plus h is equal to the same is equal to the autocovariance for any other h shift in our time points. So in this particular case, I showed 0 and h. The key is this is for all t, all time points. So what this means then is that the mean and the autocovariance are not functions of t. They're always going to be the same as long as we have, at least with the autocovariance there, that h lag time shift. Now, excuse me, what this then is going to mean for us with respect to the autocovariance, we're going to be able to simplify the notation behind it, because no longer are we worried about what time are we at. Rather, we're only going to be worried about that h lag time shift. So now our autocovariance in a weakly time series, weakly stationary time series setting can be just simply denoted by gamma of h. Note then that the variance of x of t then is gamma of 0, because again that would mean I have something like this, gamma of t and t. There is no time shift. Then what about our autocorrelation function? Well, we can also do a similar notational change to it. Now we can work with, let's say, just rho of h, because now I don't need to know what the time point is. I only need to know that h lag time shift itself. And so what happens then is that our autocorrelation function simplifies down to gamma of h divided by gamma of 0, because of course we would only need gamma of 0 there in that denominator for that variance, because that variance is not dependent upon a time shift. Now, strictly stationary is more restrictive than weakly. So if we have strictly, we get weakly. If we have weakly, we don't necessarily get stationary, except for in a special case that we'll mention shortly. Now, very often, you'll hear people when they say, they'll just simply say stationary. They won't necessarily say weakly. They won't necessarily say strictly. If they just say stationary, what they are actually referring to is weakly. It's just because this is what we typically work with most often in time series analysis, and so people don't like to put that extra word in front of it. Okay, so let's take a look at some examples. First of all, a very simple one. We'll talk about white noise. Again, white noise, we'll call the corresponding random variable W sub t. It's distributed independent normal 0 sigma squared W. Is this a weakly stationary time series? Well, we know then if Wt, and also everything's identically distributed, we know then that the expected value of xt is always equal to 0 for all t. So, okay, we got that first part done for weakly stationary. Then for the second part, with respect to the autocovariance, we know the variance for each of these Wt's is equal to sigma squared W. Also, we know that the autocovariance function, when we're not necessarily talking about the variance, is always going to be equal to 0 for any h lag time shift, because we have independence between let's say Wt and Wt plus 1, and so on. So in this particular case, we do have a weakly stationary time series. Now also, excuse me, note that the joint distribution here is the product of the one-dimensional distributions, because yt are independent, and actually you would have strictly stationary too. Okay, so let's move on to a little bit more complicated example. This deals with the moving average that we've seen previously. We have the average of these Wt values to become m sub t, and we have over 3 different time points. Now previously, we've actually found that the mean is equal to 0 for all possible t. We also found previously that the autocovariance function between s, or x of s, and x of t was found as follows there. And the key is that it didn't matter what s or t was. The only thing that ended up mattering in this, in our derivation, was how far apart is s and t. In other words, that lag. And so, is this time series weakly stationary? Well, yes, it is, because it's only dependent upon, or the autocovariance is only dependent upon that lag time shift. Okay. So, some comments. Note that gamma of h is equal to gamma of negative h. What that just, for a weakly stationary time series, what that just basically means, it doesn't matter if you're going, let's say, the difference between the two time points of interest, if it's, let's say, positive 2 or negative 2, the autocovariance is exactly the same. Now, stationarity can also be examined when 2 time series are of interest, let's say x sub t and y sub t. Now, very often, some textbooks will actually introduce the concept of stationarity in terms of two time series at the same time, what I like to do is actually break this off into a different subsection of my notes rather than do it in the middle of this section here. But just real briefly, what does it mean to have stationarity when you're dealing with two time series at exactly the same time? Well, you have weekly stationarity with respect to each individual time series as well. And to get weekly joint stationarity, then you examine something called a cross-covariance function. In other words, how is x of t related to y sub t? And you can find it as you might expect. Here's just like a regular old, how we find a covariance. But now I'm working with x of t here, and I'm working with y sub t here. And basically what we just need is that this cross-covariance function to only different values are dependent upon only of h itself. Don't worry about this right now, but I just wanted to introduce the concept. Okay, so let's take a look at an example. This example comes from Shumway and Stouffer's textbook on time series analysis. We're going to look at two different time series. X of t is going to be equal to wt plus wt minus 1, and y sub t is going to be wt minus wt minus, sometimes it's hard to say all this, w sub t minus 1, or wt is white noise. Okay, now what I want to do here is show that both of them are weekly stationary. I'm not going to worry about the joint stationarity between these two series. So the first thing that I need to do then is I need to find, well, what's the expected value of x of t? So expected value of x of t, I just simply plug in what x of t is inside the expectation. Then I apply, again, what we get from a mathematical statistics course. I can bring that expectation inside the sum so that I have them separate like this. Each of those expected values are 0 because they are white noise. So that means the expected value of x of t is equal to 0 for all of t. So I got the first part done to show weekly stationary. Then in terms of the autocovariance function, let's first start with gamma of s and t. So x of s, x of t, that's what I want the covariance for. I just write out what these are or what this autocovariance function is by definition. We just found the mean to be always equal to 0. So this simplifies down to simply finding expected value of x, s, and xt. Okay, so similar to what we've done previously in the notes, we write out what x of s is and what x of t is. I then multiply everything out as shown here. That's an extra parentheses that we don't need. Then we look at particular cases. What if s is actually equal to t? Well, look what happens here. If s is equal to t, I'm going to get a t here, I'm going to get a t there, a t here, and a t here. These two w's will be exactly the same, and also these two w's will be exactly the same, and so that's why I have a squared term right there. Then I can bring the expectation inside the sum, so I have expected values here. Expected value of wt squared, I can use then the formula for the variance to find what that would be. That would be the variance of wt plus expected value of wt, that whole quantity squared. The same thing then happens over here for expected value of w sub t minus 1, that quantity squared. And also what I can do here is notice that I have basically two different cases where I have wt times wt minus 1. So that's why I have a 2 there. And since the w's are independent of one another, I can bring the expectation through the product. Okay. So now what's the variance of wt? Well, sigma squared w. What's the expected value of wt itself? 0. So I have now 0 squared. Each of these expected values of the wt's are 0, 2. variance of w sub t minus 1, sigma squared w, and then expected value w sub t minus 1, that whole quantity squared, is 0 squared. So if you do the math, you get 2 sigma squared w. This is if s is equal to t. Notice how this is not dependent upon what t is. So it doesn't matter if t is equal to 1, t is equal to 2, t is equal to 3. I get exactly the same thing. Well, what about if s is equal to t minus 1? So wherever I saw an s before, I'm going to put in a t minus 1. And so now I'm looking for the autocovariance function at x of t minus 1 and x of t. Now, with this expected value here, again, I can bring it inside the sum. I can then put together, for example, we will have 2wt minus 1s there, so that becomes a square. Similar to what we just got done seeing here, I have two w's. The subscripts don't match up, and I know these w's are independent, so I can bring the expectation inside the product itself. Each of the individual expectations, though, are 0. So this becomes 0, this becomes 0. This expected value of w sub t minus 1, that w squared, becomes a variance plus an expected value squared. And then again, I can bring then the expectation through that product. And so what we end up with then is sigma squared w. Again, it doesn't matter what t is. This is always going to be exactly the same. And you could go on continuing to find some of these other expected values. And this is what you end up getting, where my autocovariance function for x of s and x of t is only dependent upon the difference between s and t. In other words, what we've been calling h, or lag difference. So therefore, x of t is indeed jointly stationary. Well, what about y sub t? Again, y sub t is wt minus wt minus 1. Well, I would like you to go through this proof on your own, and indeed, as you might expect, it is weakly stationary as well, because this autocovariance function is only dependent upon the lag value, the difference between s and t. Okay. So what we've been seeing so far with our models are a special case of a linear process. And in general, you could write out a linear process such as this. X of t is equal to, let's say, the overall grand mean for the series plus the sum from j equal negative infinity to positive infinity of psi sub j, where psi sub j is just some constant at an index j, times then my white noise at w sub t minus j. Now with this then, we also need to make sure that if I were to sum up all these psi sub j's, it's a finite value. Okay, so a very simple assumption that we need to have. So that's a very general way of looking at a linear process. So for example, we just saw this linear process where mu was equal to 0, and we see that we have some size that would be, let's say, out in front of the w's that would be equal to 1. Now the reason why this is important is that if we have a linear process that's stationary, then one can come up with a nice expression, I wouldn't call it necessarily nice, but an expression for the autocovariance function that's just dependent upon that lag difference, that h. And this is equal to sigma squared w times the sum j equal negative infinity to positive infinity, and then a product of these two constants, these psi's. So we have a general way now to find an autocovariance. So let's look at a proof of this. Now without loss of generality, I can assume that mu is equal to 0 because of course a constant like that is not going to affect what the covariance is. So back in your first mathematical statistics course, if you had something like this, let's say a random variable, we'll call it y, and I want to add, let's say, a constant 3 to it, well, then that's equal to the covariance of y. That constant just falls out. That's why I can let mu be equal to 0. So let's look at the proof. The expected value of x of t is equal to, here's what my linear process is. I'm going to put in a 0 there, and also I'm going to move that expectation, at least partially, through the sum. Then, I don't know, for some reason I decided to keep that 0 there, maybe for emphasis. I can move this expected value further through the sum. Again, the size are constants. And we know that since the w's are white noise, that expectation ends up being 0. So the expected value of x of t ends up being 0. Okay. So now let's work with that autocovariance. So I want to find the covariance of x of t and x of t plus h. So h time point shift. That's equal to the expected value of x of t and x of t plus h minus these individual expectations, which are each 0. So we're left with just expected value of x of t and x of t plus h. So I can write out my models for both x of t and x of t plus h in terms of this linear process. And then perhaps maybe the most difficult part is what's next. I want to multiply out these infinite sums to help simplify what I'm looking at. And if one were to do that, one gets this, a double expectation, where I have one of the expectations over the index I, another one over the index j, of psi of I times psi sub j times the expected value of w sub t minus I. I'm sorry, not the expected value, but just w sub t minus I times w sub t plus h minus j. And you might be thinking, oh, geez, that's complicated. It really isn't. Whenever you get some kind of big equation like this, and you need to try to simplify it, very often the best approach in any setting, especially when you're doing research, is look at a simplified case. So, for example, let's say for some reason now infinity is actually equal to positive 1. Negative infinity is actually equal to negative 1. On your own, actually plug that in to these equations. Now you're going to be working with a lot less terms. Start multiplying it out, and now you're going to see the patterns form that eventually lead you to seeing that we have this equality. So again, try that on your own. So let me do a little bit of erasing here. Actually, let me bring that up again. So now this expectation, I can bring it through the sum. Excuse me. And we're left with a lot of the stuff that we were seeing before. Let me come back up here. So when we were going through this proof for this very simple linear process, the things that matter to us is that when we multiply it out, we had the subscripts for, let me do a little bit more erasing. The thing that, really mattered to us is that when the subscripts on these w's would match up for a particular case. So when s is equal to t, I get wt squared. Otherwise, all the other expected values involving the w's, when the w's didn't have subscripts that match up, those expected values end up being 0 because of this white noise property that we have. We have these independence between the w's. So if I come down here now, what one could do is look at, well, when are these w's going to match up? Look at the subscripts here. I have a t, I have a t. So that part matches up. But what I need is this negative I and this h minus j to match up. When I have that, then I will have an expected value of some w at some index squared. And then that's going to be equal to sigma squared w. Otherwise, if negative I is not equal to h minus j, then I'm going to have two separate w's. Then when I work with the expected value, I'm going to have two separate expected values of w's, and we know those individual expected values of just a w itself is equal to 0, and so everything else ends up being a 0. So because of that then, and again, go through this on your own, try a simple case to see this, my autocovariance function ends up being this: sigma squared sub w times the sum from k equal negative infinity to positive infinity, where I just chose a different index there to work with, of psi of k and psi of k plus h. Notice time is not involved at all. I'm only worried about that h lag difference between the two different time points. So this is a very, very powerful result here. Okay, so notice I have important. So we talked about weakly stationarity and strictly stationarity, or weakly stationary and a strictly stationary time series. Now, weakly stationary does imply strictly in a special case, and that is when our time series has a multivariate normal distribution to it. And the reason being is because to fully define that multivariate normal distribution, we only need to worry about the means and the covariances. Once you have that, you have the entire distribution. You understand the entire probabilistic behavior of whatever random variables that you're talking about. And so if I'm looking at weakly stationary, of course, what I'm doing, I'm looking at the means, I'm looking at the covariance or autocovariance. And so if I get that to work out for me, then I get strictly as well. Okay, so let's end with essentially a visualization of what stationarity means. So in actual application then, we're going to have a sample, and one of the first things that we're going to do with the sample when we're dealing with time series data is plot the data over time. And let's try to visualize what that would mean, stationarity, in the concept of the actual sample. So in this particular plot here, notice how I'm having a number of time points with values kind of low relative to x of t, or the y-axis. Then I have a number of them that are kind of high. And so you might expect this, let's say, suppose I call this mu sub, what do I want to use here? We'll say mu sub A, mu sub B, where maybe we have two different time series essentially that have kind of been put together, where one has, generally speaking, if we think of the population mean, the overall mean, mu sub A is maybe right about here relative to the y-axis, and mu sub B is maybe right about here relative to the y-axis. And so we have basically two different means that perhaps ended up resulting in this actual observed time series here. So in this particular case, I would not have stationarity. Contrast to this particular setting here in terms of that mean. Notice it seems like everything's going around about 0 in terms of these observed values. And of course, we don't know exactly what mu is, but I would expect mu to be somewhere in the middle of those time points, so about 0. What we also see in this time series is that the variability seems to be constant across the different time points. And I'm basing it upon where I see where these top points and these bottom points tend to all be around about the same area there. And so, at least with respect to the variance and with respect to the mean, it looks like we have the conditions needed for weakly stationary. Now, to make an evaluation, though, of the autocovariance function when you're not talking about the variance is actually quite difficult, and you can't necessarily do it with a plot like this. We will look at other plots coming up in our course that will help you a little bit. Here's another time series. Notice how we have this trend over time. So you might be thinking, okay, that mean the true mean is actually changing over time because of that. And so this is not weakly stationary. And lastly, here's a plot of, again, another set of observations. Notice how the variance tends to be changing over time. So this is another case where we have non-stationarity. So from examining these plots, why is it important to have stationarity? Well, you can see that if your mean, if your variance is changing over time, it's going to be harder to estimate that. Also, in a big picture, in terms of the models that we're going to be constructing, we need to have consistency. You know, what happens, let's say, at time points 1 through 10, hopefully will tell us something about what's happening at time points 11 through 20. If that doesn't happen, any model that you construct is going to have difficulty dealing with the differences that occur over time. Now, fortunately, though, even if you do have non-stationarity, as shown on one of these plots, like this one, for example, there is things that you can do with your data to try to induce stationarity so that you can apply some of the models that we will be discussing. Okay, so that's a brief introduction to what stationarity is and why it's important for us when we're doing time series analysis.